Welcome back, everyone. So continuing where we left off in the last video, we see that if we heat up a gas, that gas starts to glow, emitting light. Now, if we pass that light through a prism, the prism separates the light by wavelength, and we can see the individual component colors which make up the light that was emitted by the gas. Different substances give off a different spectra when we analyze them in this way. For example, hydrogen gas, when it is heated and the light is passed through a prism, gives us the following line spectrum where we see red, orange, yellow, green, sort of a darker green, and then some blue and violet colors. But we see these large gaps in between the various colors. So that's where we're at right now. The question, though, is where do these colors come from? Why do we get these specific colors, and why are they different for different elements, and why do we have these big gaps in between the various colors? To understand that, we need to talk a little bit about quantum mechanics. In the lecture note outline packet on this page, you'll see that I've written out a description and an explanation of what I'm about to go through here. Now, if you want to write down and take notes about the part I'm about to discuss, probably what I would suggest is, before you do that, just watch and listen to what I'm about to show you, and then afterwards, pause the video, come back with a blank piece of paper, and then just jot down some notes. So let's talk about quantum mechanics a little bit. Here in our reality, where we're much bigger than electrons and molecules, we experience things in a different way than those very small things do. And the way we experience things is basically in a continuous way. What I mean by that is, say we have some kind of a weight or mass that we hold above the ground. When we drop that mass, it goes from a state of higher potential energy to lower potential energy. And as it does that, it goes through a continuous range that is an unbroken range of potential energies on its way to the ground. It's not like as the weight goes from the sky down to the ground that it jumps instantaneously from one energy to the other. It just falls continuously down, and if you watch it, you can see it sort of glide down to the ground and then hit the ground. Now, that's what our ordinary reality is like. There are some things, though, that aren't quite like this. Think about a piano, for example. A piano, of course, has white keys and black keys, and these different keys represent notes. When we go from one key to the next, we're going from one frequency to the next frequency, and we get different note sounds. But these aren't the only notes in the world. It's just that the piano keyboard is leaving off some notes because that's the convention in Western music. So for example, let's compare B versus C here. We have these two keys and they're right next to each other, and of course there's no key in between them. Does that mean there's no frequency in between those two different notes? No. Let's take a look at these notes in a little more detail to understand what's going on. Here we have B. This is actually B3, and B3 produces a wave that has a frequency of 247 cycles per second. That is to say, the waves are spaced and they're moving forward at a rate where each peak of the wave passes a point 247 times per second, or 247 hertz. So that's B. C4, also called middle C, has a frequency of 262 cycles per second. So on the piano keyboard, there's no key that we can press that will give us something in between these two notes. Something with, for example, 250 cycles per second. Our pianos are simply not tuned to that. And if someone produces a note, say with cycles of 250 per second, we would say that piano was out of tune, and we would fix it to make everything match these particular frequencies. So I'm showing you all this to help you get an analogy for things like the blank spaces on that line spectra that we saw earlier, as well as the colors. The colors are a bit like the notes on the piano keyboard. Those are allowed things that we can press a button for and get a note, or places where an electron can be energetically. The gaps in between those colors are a bit like the gaps in between the notes on the piano keyboard, where we don't have a key that we can press to give us that particular frequency. We refer to situations like this, like the one we see here on the piano keyboard, as being quantized. When something is quantized, we go from one value to the next value like we would through a staircase. There are only certain allowed values, and we go from one to the other by jumping between. This is different than something that's continuous, like a ramp, where we go through a smooth range of values from one to the next. So let's take these analogies down to the microscopic level, where we're going to talk about electrons and atoms. It turns out that things that are very small, like electrons and atoms, live in a world that's mostly quantized. Electrons, for example, can and do exist outside of the nucleus of the atom. It turns out, however, that electrons cannot exist just anywhere outside of the atom. They have to exist in certain well-defined places with very specific energies. The situation for the electron is a lot like this. The electron can exist at certain energy levels depending on the type of atom that it's around. And it turns out that we can look at the line spectra that atomic emissions give us to actually figure out where the electron can be at. It's a bit like looking at a line spectra, looking at the colors, and figuring out what notes an electron can play depending on what atom it's in. To help you better understand where these colors come from and why we have these empty gaps in between the colors, let me show you a visual analogy for what's going on around the atom when we heat it up and get these colors. To understand what's going on when we get the atomic emission spectra, we have to think about what's happening when we heat up the gas molecules. When we heat up a gas, we're providing energy to that gas. And what that actually does is it excites the electron that's orbiting around the nucleus of the atom. When that electron is excited, it goes to a higher energy level. You can think about this like the electron is playing a higher note on the keyboard because it has a higher frequency. We can also think about this in terms of a spatial analogy. The farther away an electron is from the nucleus of an atom, the higher energy that electron has. So anyway, we heat up this atom and the electron gets farther away from the nucleus, it has a higher energy, and it has a higher frequency. So what happens then? Well, as the electron is heated up, it actually wants to fall back down to a lower energy state again. That's the natural order of events in the universe. What goes up must come down. Now, when the electron comes back down in energy from that higher state to the lower state, something very special happens. As the electron falls back down in energy from this state of higher potential energy to a state of lower potential energy, it has to give some energy off. This is just like if we roll a ball down a hill. It starts off with a high potential energy and then it ends with a lower potential energy, but it has to shed all of this extra energy as kinetic energy. So when we go from a state of higher energy to a state of lower energy, energy must be released so that we can conserve all of that energy. Now, how does the electron actually get rid of energy? Well, it's really cool. What it does is gives off a photon. It gives off light. And that little photon that the electron emits as it falls down in energy has a very specific energy. It happens to have exactly the amount of energy as the difference between the two energy levels that the electron is at. So for example, if the electron falls from this level 2 to level 1, there's some delta energy there, some change in energy. And as the photon exits the system, it carries with it that exact amount of energy. So this photon has an energy, but what does that even mean? Well, to understand what that means, we have to remember that these different colors that we see in the line spectra each have different energies. And the energy of these colors is based on their wavelength. So it's kind of like saying wavelength and energy are one of the same thing. It's sort of two sides of the same coin. I'll go over that concept again in a few minutes, but for now, let's go back to this photon. The photon is emitted when an excited electron falls down in energy. When this electron relaxes from a higher energy state to a lower energy state, the difference in energy is given off as a photon. The color of this photon, that is to say its wavelength, exactly equals the change in energy experienced by the electron. Let's take a look at another image I have over here, which tries to show how we get different colors from the electron relaxing from different energy levels. Now, before anything happens, we have an atom in the ground state. That is to say that the electron is in the lowest available energy level closest to the nucleus, orbiting around it. Then, when we do something to heat this gas up, like flip the switch on that device I showed you earlier, where we pass electricity through the glass tube which contains the gas, what happens is the electron gains energy and it's excited to a higher energy state. Now, depending on the type of atom we have, there are certain energy states that electron can be at. These are like keys on a piano keyboard. Now, the specifics of where those energies are and all of that stuff basically depends on the nucleus of the atom and how many electrons there are around it. But let's just do a simplification of this. Let's take a look at this system where we have one proton and one electron, and let's assume there are 4 energy levels allowed for that electron outside of the nucleus. So the electron can be at this first energy level that I've called n is equal to 1. It could also be at the second energy level. This is called the second excited state, where n is equal to 2. It could also be at the third excited state, where n is equal to 3, or the fourth excited state, where n is equal to 4. Now, how does the electron get to those excited states? Well, as I was saying earlier, it's when we heat up the gas of hydrogen. When we heat up hydrogen, the electron is promoted to one of these higher energy states based on how much energy we provide. So let's assume for a minute that we just go to this first excited state, so not that far away from the nucleus. This is n is equal to 2. This is called absorption because the electron has absorbed some energy and is promoted to that higher energy state. So far, we haven't produced any colors. All we've done is absorb energy. But this is where the interesting thing happens. The electron, now that it's excited to this higher energy state, is unstable, and naturally it will fall back down to the lower energy or more stable state that it can. And in this case, it's n is equal to 1, let's say. So if the electron falls back down from n is equal to 2 to n is equal to 1, it gives off a wavelength of light, which happens to be, as I've shown here in this example, red. Now, how do I know it's red? Well, I'm simplifying things here a little bit, but suppose we wanted to figure out the difference in energy between these two states. What we would do is look at the color that's producing that, and we would find its wavelength. So we would find the wavelength of red. We would then do some kind of calculation to figure out what E is equal to when we have a wavelength of red, and then we would say, well, the electron is moving between 2 energy levels that gives off that gap. So we can figure out the gap in energy by looking at the wavelength of color, which in this case we see is red. Now, what about the other energy levels? How do we know what that difference is? Well, basically what we do is we look at the different colors and we say, what are their wavelengths? And then from that, we can figure out how far the electron has fallen. So for example, if we go from n is equal to 3 to n is equal to 1, we get a shorter wavelength, something between red and blue. It has more energy. And that's because the gap in energy between these two states is larger. Notice here the largest gap that I've shown gives off the shortest wavelength, or almost the shortest wavelength, close to purple. We're getting close to that ultraviolet region with shortened wavelengths. Why is that? Well, that's a very large transition in energy. Think about how much energy we must have provided to excite the electron from this lower energy state way up there. All of that energy needs to be given off when it falls back down to the ground state. So this is where we get these different colors. Now, what about these gaps? What do these gaps represent? Well, actually, they represent nothing. They represent places where the electron cannot be. These are like the missing keys on the keyboard. We simply don't have any allowed energy levels for the electrons at any of the wavelengths that we don't see here. That's what those gaps mean. Something very interesting to think about, though. The fact that the electron can transition from, say, the red energy level to this teal energy level, but doesn't go anywhere in between, is very interesting. It means that it goes through these different energies, much like a skateboarder would when it goes down some stairs or up some stairs. It doesn't go in between them, it just jumps from one to the next. It's a little bit like teleporting, which is very interesting. Now, all of this information that I've just conveyed to you about how we can correlate the line spectra and the colors and the energies of that light back to what the electron is doing around an atom is something that was developed in the early 1900s, which, if you think about it, isn't very long ago. And it's something that we call the Bohr model of the atom. Now we're going to go on to the next page and talk a little bit more about the Bohr model of the atom and write down some notes so we can use this to do some more stuff with electronic configurations. So in the Bohr model of the atom, we have a nucleus in the center and electrons are outside of it, but instead of being able to be anywhere, the electrons are said to be at quantized energy levels, and we can actually figure out the difference in energy between those quantized energy levels by looking at line spectra. Now, we're not going to be looking at line spectra or doing any of those calculations, but what we will be doing is drawing some qualitative diagrams to figure out certain things that we want to know. One of the first things that I want to teach you about with the Bohr model of the atom, though, is something called the principal quantum number, which we give the symbol n. The principal quantum number with the symbol n can have integer values above 0. So for instance, they could be n is equal to 1, n is equal to 2, n is equal to 3, and so on, but nothing in between. This principal quantum number is used to refer to the energy levels outside of the nucleus where the electron can exist. So when we're looking at atoms a little bit later on, every electron around an atom is going to have a principal quantum number, and that principal quantum number is really important because it tells us how much energy that electron has. So an electron with a principal quantum number of 1 has a lower energy than an electron that has a principal quantum number of 2, and so on. These energy levels, where we're increasing the principal quantum number outside of the nucleus, are called the Bohr energy levels, or simply just the energy levels of the electron. So now that we know that electrons can have these different energy levels with different principal quantum numbers, we can also talk about the difference between ground state and excited state electrons, and the difference between absorption and emission of energy. When an electron is at the lowest possible energy state outside of the nucleus, it is said to be in the ground state. Soon you'll be learning these specific rules that allow you to predict the ground state configuration of an atom, but for now note that essentially what we want to do is put an electron in the lowest available quantum number, that is to say, lower values of n. Atoms, however, are not always in their ground states. For example, when we heat a substance up, or when we illuminate it with ultraviolet radiation, we're doing things that excite the electrons around the nucleus of the atom. We want to make sure we're really clear when we say things like ground state, excited state, and absorption, as well as emission. As I was mentioning, the ground state configuration for an atom places the electrons into the lowest available energy level, the lowest available quantum number. So let's suppose we have an electron in the ground state, and the energies I have available are n equals 1, n is equal to 2, n is equal to 3, and so on. We would put the electron, which I'm representing here with a green sphere, in this n is equal to 1 because that's the lowest one available. Now, this particular electron could be excited into various excited states, like n is equal to 2, or n is equal to 3, or n is equal to 4. Let's just pick one of those. Say, for example, n is equal to 2. If the electron is promoted into n is equal to 2, we call this an excited state because the electron is not in the lowest available energy level. How does an electron enter into an excited state? This is called an absorption process, because in order for the electron to be promoted, the atom must absorb some energy. How much energy? Well, exactly the amount of energy that's necessary to raise the electron from n is equal to 1 to n is equal to 2. If not quite enough energy is provided, so the delta E is a little bit smaller than this delta E1, what happens is the electron doesn't get excited to that first excited state. So this process is called absorption. Now, once the electron is in the excited state, it will relax down to the lowest energy state, that is the ground state. When this happens, when the electron relaxes to the ground state, some kind of energy must be released. We call that emission. The emission, in fact, is a photon, and this photon has a wavelength, or you could think of it as a color, that's directly related to the difference in energy between the excited state and the ground state. So an atomic absorption process is one in which the atom is excited by some external amount of energy. That energy is put into the electron, which is promoted to a higher energy state, or a higher principal quantum number. This is called absorption. From this excited state, the electron can relax back down to a lower energy state, such as the ground state. When this happens, the electron releases energy. We call this process emission. By looking at the wavelengths of light that are emitted from the electron when it relaxes from the excited state back down to the ground state, we can determine things like the difference in energy between the excited and the ground states. Let's go into the next page and wrap up with a few points about all of these concepts, and I'll tell you a little bit about what we're going to do next. So I'm going to wrap up the video lesson here in this part of the lecture note outline, where I'm just summarizing stuff about absorption and emission spectroscopy. So various things are pointed out here about where the line spectrum originates from and what it means, the difference between absorption and emission, etc. And then I ask a final question here, which is, why, after we read through all these, why do we only see discrete spectra, that is line spectra, when we do things with atoms like heat them up and then we look at what colors they give off? Why don't we see a continuous rainbow? So that's a really good question, and we definitely talked about that a little earlier in the lesson, but I think it'd be a really good point for you to sort of reinforce that concept by trying to phrase this in your own words. Feel free, of course, to let me know if you have any questions about that. I'd be glad to help you. Now, what are we going to do next? Well, in the next video lesson, we're going to start off here in Part C. And in Part C, we're going to be talking about the wave nature of the electron. And specifically, we're going to be building up a conceptual understanding of how electrons are arranged around various atoms. And to do that, I'm going to introduce you to something called the Schrödinger wave equation the next time. Now, first off, don't worry, we're not going to be solving this equation or doing any math. But what I am going to teach you about is what this equation actually provides to us, and then we're going to use that information to do what I was just talking about. We're going to build up a picture of the electrons around different atoms. And from there, we'll be able to do a lot of really neat things, like predict, for instance, the three-dimensional shapes of molecules, understand why we have fixed charge metals versus variably charged metals, and why we get the charges that we do. So with that, I'm going to end this lesson. I hope you're doing well. Please let me know if you have any questions, and I will see you soon. Take care.